All right, so let's talk about 104 here, analyzing input data. This is all about how to massage input data to make it useful, and this is where a lot of the work is at. The actual model, as you can see, is half a dozen lines of Python, choosing a standard algorithm from a relatively small set of algorithms, but preparing the data can be quite a task. And so here, we get data, and this data is data about housing prices in California. They broke California into zones that I guess are smaller than counties, but they're geographical zones throughout the state. They call them districts. And there's a whole bunch of information about each district, including the average housing price. And they would like to predict housing prices from that. So when you input the data, you can use the info function here. So you load housing data here, you download it from the web. It's a zip file, and this will unzip it and put it in a thing called a data set. And now you can use the info feature to get a summary of it, and this shows you what the categories are. So you have latitude and longitude, the age of the house, the total number of rooms and the total number of bedrooms, the population and the total number of households, the median income, and the house value, which is the thing we're trying to predict, and then a non-numeric field called ocean proximity. So those are the 10 attributes of each instance we had here. And we'd like to learn which of those are predictive of income. And so head, just like it does in command line Unix, will show you the first few records. This shows you the first 5 rows of data, so you can see total number of rooms, total bedrooms, population, income, ocean proximity, and so on. Notice here, you get an idea what the ocean proximity is like. It's this phrase, like near a bay or something, not a number. So you can get categories and counts this way. To see what's going on with that ocean proximity field, it only has 5 possible values, and here's the values, and here's the number of instances with those values. Then you can do describe, that will give you statistics of all the numeric fields like mean and standard deviation and so on. And so then you can make histograms, plotting them to help you understand how to use the data. And so here you see longitude and latitude have 2 peaks because, as you can imagine, pretty much all the houses are either in the South Bay near Los Angeles, or in the south part of California near Los Angeles, or they're up near San Francisco, and there's not much happening anywhere else. So it's a 2-peak distribution. Here's the total number of rooms and total bedrooms. Those look like pretty common Poisson distributions. And median age seems to be all over the place. But here you can begin to observe some flaws in the data. There seems to be a huge spike at 50. So that suggests that this data is not accurate. They chose off a list of possible values, and 50 probably means 50 or more years old, not really the number 50. So that's a thing to be aware of. And here you've got income, households, and house value. And house value also seems to just hit a peak at 500,000 and not go any higher. So again, this spike of data here is probably not really accurate. And this is what you have to do when massaging data, which is why it is not very scientific. It's more of an art than a science. You have to make judgments about what parts of the data you trust and what parts of the data you don't trust. And whenever I listen to political pollists trying to predict who's going to win the next election, they describe how we had to increase this, we had to disregard that, we had to fill in this missing stuff here. It's not as precise as you might hope it would be. So here if you create a training and test set, you can shuffle it and randomly choose 80% to be training and 20% to be test. And that might seem like the best thing to do, but it's going to turn out this is not the best thing to do for this kind of data, or for that matter for political polling. So here's the training set, and the training set is 16,000 and the test set is 4,000. And here's the test set showing these values. And if you run it again, you're going to get a different random set. It's a random set every time. All right. Now this is a problem because you might have biased samples. So consider this. If you have a survey of 1,000 people and you're measuring something that is related to their sex. In the U.S. population, 51% of the population is female and the rest are male. So if you choose a random sample and plot out the histogram, your random sample is most likely to have 51%, but it is most of the time the most likely particular value is 51%, but it's only 17% likely that you're going to get that. It's quite likely that you're going to get quite a different number, like 53% or 49% women in the sample. And that might mean that your random sample is in fact skewed and not representative of the population. So the solution for this is what they call stratified sampling. Instead of randomly choosing instances, you take the parameter that you believe is highly important and you break it into bins, like 5 bins. This is the median income. We have a strong belief that median income probably affects the housing price. So rather than randomly choosing samples and perhaps having a skewed sample of median income, we're going to bin the median income into bins and then choose exactly the right number within each bin of random samples to represent it correctly. That's called stratified sampling. And now you'll get records, and although they are random, and if you do it again, you'll get a different random sample, if you compare the actual statistics, it will always have the right percentage in each of those bins. And this is something people do in political polling too for the same reason. All right. And so now, if you compare this, here's the training set and the test set. You can see that category 3 should have 35%, and the test set has 35 and 31 and 17, down to a percent. Now the training set and the test set are very similar in all these ways to make sure that you haven't chosen a randomly unlucky data set, which would skew the answers. And the unstratified data set, C, had more changes. You have 35% but 34% here, 31 but 32 there, and so on. So if this is an important variable, that source of noise is undesirable, and you're wiser to use stratified sampling. So that's one issue. Then there's an income category column. We're going to remove it and plot it. I think we removed it because we included a binned version of it somewhere. I think I've forgotten exactly why. Anyway, now you can plot it. So you can plot the data here, making a scatter plot with latitude and longitude. And this will just show you the location of all these zones. But the problem is in the San Francisco Bay Area and in the Los Angeles area, there are so many zones packed so closely together that it just turns into a featureless blob. You don't know how many blue dots are piled on top of each other here. So what's better is to use transparent dots. Now you can get more of a clue. And now you can add more data. You can use dot size to represent population and color to represent the house value. And now you get a much more informative plot that shows you red is the most expensive houses. So the most expensive houses are, of course, on the coast in San Francisco and on the coast in LA. And inland is cheaper. And you get a lot more information here, just ways to represent data. And then there's more cleaning up of the data to be done, and you can do that with correlations. If you calculate correlation coefficients, the correlation coefficient tells you how much each one of these pieces of data is predictive of the housing value. So of course, housing value is 100% predictive of housing value. And you notice income is very strongly predictive, 68%, total number of rooms to some extent, and median age to some extent, but the rest is not very predictive at all, except, of course, for latitude, and therefore I would imagine longitude. I guess latitude mainly, because latitude tells you about north-south location, and as you've seen, if you move to the cities, you have much more expensive houses than moving to the country, and the latitude will do that. So what you see here is median income, total rooms, and housing median age are positively correlated. And so a scatter plot would be more informative here. So here you have the histogram of median house value, and here you have median house value on the y-axis and median income on the x-axis, so you can see that as income rises, house value rises, and this is a strong correlation. There's a strong relationship here. Here is a weaker relationship. Here there's almost none at all. and those are total rooms and median age. So you can get some idea what's going on there. And if you want to look at median income and median house value in more detail, you can zoom in on that. And now you notice the kind of stuff that you have to do this data analysis to understand. Notice that there is some kind of quantization here. The house values are 500, 450, 350. These lines mean a preponderance of data there. So apparently they've rounded off the house values here, and these numbers are not really accurate. And then there's the big ram up of way too much data here, because apparently this is the largest permissible number and all larger numbers are collapsed into here. So those are some defects in the data. It might be best to remove the districts on those lines to avoid having your model try to predict this lumpy distribution, which is probably not really true of the actual house values. All right.
Excuse me, sir.
Yeah.
Sorry.
Yeah.
So what's the original label of in this data?
Well, it came from some kind of, I think, government statistics or something. But this, by the way, is often the case.
No, I'm saying the label. Like you are trying to predict something. It's supervised, right? So
yes. Yeah, we're trying to predict house value, median house value. And this is the sort of thing you might do for an insurance company, right? Determining how much to charge for insurance rates in these various districts. Which, by the way, is currently a problem. If you live in California, there's a huge problem. You can't get housing insurance anymore. I couldn't even get renter's insurance easily because of all the recent wildfires have made it so dangerous to have a house in California that all the insurance companies have stopped selling policies here because their old models of risk no longer work, and they don't yet have enough data to form the new model of risk. So they don't know how much to charge you. And so that's one application. Anyway, I'm not sure if I answered your question entirely. Did you get your answer?
Because no, I'm just trying to understand. I mean, from the features that you provided in the beginning,
yeah,
which was the label, and
yeah,
the rest of the features. Why do I care about the features if I am having the label and I want to predict something?
Yeah, because we're going to try to. We have some data with labels, and we're trying to train a model so we can predict unlabeled data from it. That's the way it always is. So you have some data set that came from somewhere, and you want to, after training the model, you'll want to apply it to other districts where you don't have the label. And in this case, I'm not sure that's terribly realistic, but that's what we're doing. We're making a model to predict one value from the others.
So the label is the median house value?
Yes. Yeah, that's the thing we're going to try to predict. So we start with data that has it to train a model, and then we can test it on others. This is what you're doing in all these cases. We're actually not accomplishing anything new. We're taking a labeled data set and training a model and seeing how well it predicts the test set we set aside for a labeled data set. So what we're doing is studying the ability of the model to do the job. We're not applying it to actual external data. That would be the next step. And here's an important thing. It turns out that you can combine attributes and make a more important attribute. So here, we're going to take rooms per house divided by total rooms, and this is going to be, rooms per house is rooms over households, and bedrooms is how many bedrooms over total rooms, and people per house is population over number of houses. So these combined features made by combining two of these others might well be more important, and indeed they are. Notice down here, you make the attribute combinations, and now when you do the correlations, you find that rooms per house is strongly predictive, 14%, even though rooms is less and total households is less. So this is fairly common, as you can imagine, that a combination of attributes gets an attribute that is more directly predictive. And we're going to see this come back a lot later. You often combine attributes to make a new synthetic attribute, and that turns out to be more useful because it's more predictive, and often it has a nice simple relationship to your desired goal, like linear. So these are some of the manipulations you typically do on data. And we didn't even get to fitting a model yet, but this is a lot of the pre-processing you have to do. So you get a little practice at learning some of the tools that help you pre-process data.